Okay, so how are we going to make this new thing? That's the next question. Well, we know some of the things that this new thing has to do. It has to measure power consumption. That's pretty obvious, right? But the really big thing is that it has to make it easier to gather that data. So how are we going to do this? First, to measure power consumption, I use an inductive coil. And this is a little complex. If you're curious to know how this works a little bit more detail, you can ask me after. It's not really that interesting, honestly. This is the interesting part. And you've probably seen these crop up in too many presentations already. But there we go, the RF, the XB radio. And the great thing about radios in general is that they basically do what we want. They have a many to one. They can work that way. So you can have sort of your user at the center, and you can have it ringed by all these other devices that talk into that center. So the center doesn't really have to do any work. It just sits there and listens. So combining these ideas together, you basically get two pieces. You get the monitoring units, which again are made up of a radio, a power measuring circuit, and the inductive coil. And that looks, the form factor would be sort of like a kilowatt. You'd plug it in, you could plug whatever device you need into that. And then you have a collector that'll basically collect all the information being broadcast by all the monitoring units. So we have our house again. We installed this new thing. I need a name if anybody pops into their head, by the way. Super awesome. Yeah, right. So all these guys can broadcast how much the device that's plugged into them is using, and that gets collected in the collector. And that information then basically can be visualized in this way, very similar to the super awesome power bill. One of the additions, though, that's interesting is that you can actually see the current amount of electricity that your house is using. So you can literally see, if you, turn on your toaster, you'll see like, boom. You'll see it appear. And so you get all these same features as you did with the super awesome power bill. So having conceived of this idea, I then had to make it. And so this is what it looked like. This was a device on a proto board, and then my collector is basically my computer with an XB radio plugged into it. And I did a whole lot of testing, and this is a very, I probably have checked out, I would check out like 10 clip lights at a time to sort of get this, to power this thing. So I did a whole bunch of testing on the floor with this. And, in a classroom setting, you get something like this. If you had 2 power strips in the classroom, I'd put them on 2 power strips, maybe put it on the computer, and then I just have a set of lights to test. And you can literally see, when somebody plugs their computer in or when somebody unplugs their computer. You can see that the computer basically uses a continuous amount of power. So you get a lot of feedback immediately. So then I wanted to step back a little bit, and I had to ask, the point of this whole system is to decrease consumption, but I'm building a whole new system. Is this not just going to add, more than it's going to basically allow us to reduce our consumption? So how much does it cost to run? And my sort of rough estimate is that the capital cost, how much it would cost to buy this system, would be about $150, and that would be 12 of those little monitors at $10 each, and then 1 collector at $30. So the capital cost really isn't that high if you think of it over a long period of time, but how much extra electricity does it take to run this system? That's sort of the operating cost. And it's very low, actually. I estimate it's only about 5 cents for every $100 you spend on electricity. So what are the potential benefits for this system? Well, this is a typical kind of user scenario. Again, getting back to the computer. 1 month, you don't turn off your computer at all, and say that costs you $10. The next month, you only turn it on when you need it, and then it only costs you $4. And again, when it's quantitative, you're much more likely to make that change in behavior, and not only make it, but to maintain that change in behavior. But I want to emphasize that this isn't just solely about sort of conservation. It's about a whole number of other things. And one example is that in New York City, you often find that you'll have more than one company in a given area. And they'll share an electric bill, which is, say, $300. But of course, each of these companies is doing something different. And they may have the problem of how do you split up that electric bill? Well, with this kind of a system, you can isolate each company, and you can figure out the proportions that they owe in the electric bill. And so in this case, company A may say, hey, why what is it that's $150 that we're spending, and company B is only spending $50? And this is a way that the more information you have, the more questions users can begin to ask, and the more potential they have for finding inefficiencies, for saving power. Another example is that you may be in situations where you only have a limited supply of energy. So you may be off the grid and you're using a 1,500 watt generator, or you're using solar panels that give a varying amount of power. And you may have a whole bunch of things that you're trying to run, like lighting, computers, a printer, power tools. And the total load of that may be 3,000 watts, maybe far in excess of the amount of potential, of the amount of supply that you have. And you have a problem because if you overload the system, you may burn out the generator, you may brown out things. So this kind of a system is a way that you can tell exactly how much power you're using at a given time, and so you can plan accordingly. So just to summarize, the capital cost is about $150 a year, I would estimate. Excuse me, that's a one-time. Operating costs only about $1 a year. And at this point, although we haven't really used it enough to really quantify the benefit, we do know that feedback will definitely improve usage patterns. It'll definitely enable you to cut down your usage of power. And in general, it just gives you a very detailed accounting of consumption, which can be used in any number of ways, as the last two examples showed. And in summary, I really want to emphasize something, which is that conservation in general, and I don't think this applies just to energy, but I think it applies to materials and all sorts of other things. Conservation is an active relationship. It's not a passive thing. It's not something that you just start and then it just keeps on going on its own. You need to constantly be putting work into that. But that requires detailed information. That requires intelligence and knowledge. And so you need tools like this to help you do that. So what's next with this? Well, what we're going to try to do at the ITP show is I'm going to pick 4 or 5 projects that sort of all have different power consumption needs. And I'm going to try to do, again, a visualization of how much power they're using at the moment and how much power they've used over the whole show, and then also a usage graph. So you can see, who shut their project off overnight, who didn't. This sort of stuff. It'll also be interesting to see certain projects that the amount of power they consume is very proportional to the amount of activity that's involved with them. And see, with Cousteau, which is sort of an interactive sculpture, is it consuming more when there's a lot of people on the floor? Is it consuming less when there's nobody on the floor? So these are the kind of things that you can peer into with this system. This summer, we're going to be trying to test this on the floor a bit more rigorously. And then in late August, this project is sort of the foundation of a talk we'll be giving at the O'Reilly Energy Innovation Conference. And I'm going to be doing that along with Tom Igoe, Jeff Feddersen, Eric Bouygues, and Rafi. And, of course, soon we hope. So I want to send a big thanks to Tom Igoe, Jeff Feddersen, and Eric Bouygues, especially Eric Bouygues. He's been the soul of this project. He's helped me a lot. And a thanks to a whole bunch of other people. So thank you. Yeah, yeah. I mean, I think, one of the things is that I think energy is a lot about incentives. And, as much as we don't always like to talk about cost, that's what people respond to. But it's also the case that, energy is an abstract concept. And especially when, you get just one number for your whole house, it's very difficult to break it down. And I think the more you break down the problem and the more it's sort of real time so people can see the impact of their actions, the more they're intrigued to make further actions. And so I think, it's interesting. I'll share a quote which Alison Woodruff, who works at Intel Research, was here a few weeks ago. And she was talking about how she's just completed a study on people that live in sustainable houses. And she said that one of the big themes that she heard a lot was that living in a sustainable house is like living on a ship. And that's because it's active, it's work. You don't go sailing and just expect the boat to sail itself. Every step of the way, you need to do work. But she said that a lot of these people felt that that relationship was difficult because they didn't have the information. They found it difficult to really tell quantitatively what impact their actions were having. And so that's a big part of this, is trying to give people those tools so they can make better judgments.
One thing you didn't factor in was the cost of couples therapy for screaming at each other. So have you thought about maybe integrating with other social objects to proactively go ahead and turn the thing off?
Yeah, absolutely. I mean, that's sort of a way further thing, which is the idea that this is sort of a parasitic system, and you sort of would like this thing either in the outlet or in the device. And once it's in the device, like you're saying, I mean, that device can do all kinds of things. You could send that device a message, hey, shut yourself off. So yeah, that's something further out. Clay?
Since energy is a commodity, if one individual or group lowers their consumption, aren't they just subsidizing the price with no net change in the overall consumption? I've never understood this business of conserving energy by a person.
Right. Well, I mean, I think one of the things that's important, and again, I think some of the later slides show this, that conservation is one aspect of this, but there are a lot of situations, and increasingly as sort of the power grid becomes potentially more decentralized, and people are sort of relying on solar panels more, or they're relying on smaller power stations. You're going to need to be a lot more active. And you're going to need to have a lot more intelligence to know, how much you have and how you can use it. Because that's the problem right now. Basically, there's these giant power plants that just pump power out. And so what you're saying is that's kind of a result of the current architecture of the electrical system. But as that potentially evolves, it won't be that way anymore. Because, you can already, if you have solar panels, I mean, they do this at Habana Alpass, you can sell power back and make money that way. So I think that there will absolutely be incentives to save as the system changes. Thank you.